The Saturn V rocket during stage 1 of its flight reduces its mass from 2.3 million kilograms to 0.48 million kilograms over a time of 2 minutes and 42 seconds by burning off a fuel called RP1LOX. The fuel is ejected at a speed of 3,124 meters per second. What is the acceleration of the rocket? Okay, so we have two forces here acting on the rocket: its weight and the thrust here from the ejection of the fuel. That's easy to work out. That is the mass of the fuel ejected per second times the velocity at which it's ejected at. So in this case we have to work out what the mass is, and then we have to multiply that by the velocity, which we're told is 3124. Now how can we get the mass per second? Well, let's work out how much that is. 2.3 minus 0.48. So over the 2 minutes and 42 seconds it loses 1.82 million kilograms, and that took 2 minutes and 42 seconds. So per second it lost 11,234.567. So 11,235. 11235. Times 3124. So that is a huge thrust, as it should be. 1, 2, 3, 4, 5, 6. 35.1 mega newtons. So that's a huge amount of thrust. Okay, so Newton said F equals ma, so T minus W equals ma. So T minus W over m is the A. Now this looks okay. I mean, we know the T, just worked it out. And we can know the weight. That's just mg over m. But then we realize we have a problem. Although we know the T, it seems like we know the m, but we don't quite know it, because what's happening here is that the m is changing. First it's 2.3, first the fuel is 2.3 times 10 to the 6, and then finally the fuel is 0.48 times 10 to the 6. Sorry, the fuel isn't that. 2.3 times 10 to the 6 is the mass of the rocket at the beginning, and 0.48 times 10 to the 6 is the mass of the rocket after 2 minutes 42 seconds. So the difference is obviously fuel. I suppose parts of the rocket could have fallen off, but we'll assume it's that is fuel. So we have two masses here. Do we use the mass at the beginning, or do we use the mass at the end? No, if we want to be a bit more accurate, maybe we should just use the average mass. So we can say that the mass is approximately 2.3 plus 0.48 over 2 times 10 to the 6 kilograms. So what will that be now? That would be 2.78 over 2 times 10 to the 6, which is 1.39, because 1.35, that's 2.7, yeah, 1.39 times 10 to the 6 kilograms. So we'll approximate the mass to be this number here. It's changing, so we'll assume it's on average this number here. Okay, so we have answer minus 1.39 times 10 to the power of 6 times 9.81 all over 1.39 times 10 to the power of 6. So the acceleration is 15.44 meters per second squared. So remember, downwards gravity is 9.81 meters per second squared, so it's equivalent to the rocket falling upwards at a rate of acceleration 50% greater than what it would be doing if it was falling downwards under its own weight, which is pretty significant, because if you think about how fast and how much speed something can gain when it's free falling, even for 10-20 seconds, you can see that very quickly the rocket's going to build up a huge speed here. So 15.44.